Okay? That light travels in straight lines. Okay. That light rays do not interfere with other light rays. Okay, and so yesterday I had one of those flashlights. I could take off its cover, and the bare light shone light around the room, and we all saw it from all these different locations. Okay? And it had a pattern for the light. If I had a source like this, okay, the light rays went like this, okay, away from it. Right? So we say, there are a bunch of light rays that are leaving the source. Okay? They have this pattern. We'd say light rays are diverging from the source. Okay? How do we know those light rays were there? Because we could see the source. We could see it. And which way did we point our eye when we were looking at it? Towards the source. If the source was in the middle of the room and I look that way, do I see light rays coming directly from the source?
Probably not.
Yeah, no, we didn't. Okay, so that's how we know we have that pattern, right? Okay, because when we look at something, we can see it. Now, just a minute ago, I stuck one of those things that we use to hit the tuning forks in a clamp over there. Can you see it? No? Can you see it? Yes? Yes? When you see it, which way do you look? Actually, can you point at it? I see it right there. Where do you stick your arm out? Point at it. Where is it? Okay. Look at. No, you're not sticking. You're sticking your thumb out. You're sticking your point like that. Down. Down. Yeah. Oh, cool. Very good. Keep going. Okay. Hold it. Yeah. Which way? Look around and see how everybody's pointing. Yeah. Okay. So we're pointing directly at the light, or directly at that. Why do you think you see it there? With regard to the light, what are you looking at?
The light rays reflecting off the source.
Is this a source?
No, it's not the opposite.
Well, light rays that are reflecting off the object. Okay? And the light rays that are reflecting off the object, does the pattern look like this or does it look like something else? Opposite? Actually, our fingers were opposite of this. Right? So we'll say, here's the source, or here's the object. Okay? And when we had a pattern that looked like this. Okay, we were pointing at it, okay? If you're over here and you're pointing at this, what did you see? What did it look like when you were pointing at it? When you point at it now, if you point at it, what does it look like is over there? A ball on a stick, right? It looks like a ball on a stick. And so the reason you can see that ball on a stick is because, what about light? Is light going this way? The light Okay? So there's light reflecting off of the ball on a stick going the other way. And the reason you know it's there, I told you. Would you, if I didn't tell you, would you be able to know that it's there? You see it, right? Okay, you see it, right? So what we've got are these light rays that are going like this. Okay? For terminology, we'd say that's a light ray. Okay? And this thing over here is a line of sight. Okay? And I'm drawing them the way I believe your book draws them. This is pretty standard. You draw light rays as a solid line, and then the lines of sight are a dotted line. Okay? And the lines of sight is what you're looking at, and usually, often, the line of sight follows a light ray. You look that way, and the light ray you see is going the other way. Okay? Yeah? Cool. So, if I look around, when we see the object, what we're really seeing is these light rays that are coming off the object. The light rays are diverging away from the object. And actually, the object in a well-lit room, okay, looks like a source, okay, because it's giving off these light rays in all these different directions. Yeah? Okay, cool. So, all right, so that's an object. We talked about what happens when light hits when light hits something like a box or a piece of paper plastic. We talked about it being blocked, but we talked about it also being scattered. Okay? So, one of the things we can do, we can say, all right, if I have, say, an object like this, okay, and I'm going to sort of do this over here, and if you're not sitting where you can see it, then move, okay? But I'm going to take the laser, and the laser, as we saw last night, emits this beam of light, okay? And I was shining it on the board. You can see where it hit the board. What I'm going to do is tilt the laser so that it begins to hit the edge of this eraser, okay? And we'll see what happens to the beam, okay? So I'm moving it down, and I hit the eraser, and I move. Notice what's going on with the beam? What do you see happening? When I hit the eraser, can you see the beam at all? Okay, where is it?
On the other side of you.
On the other side?
Of you. We just saw your back.
You just said, oh, yeah, I told you you can't see. Move. Okay, so move.
Okay.
Yeah, yeah. Okay, it might not be far enough. You might have to move a little more. Okay, so the laser beam's going like that, and then you see it on the eraser, right? Okay. All right. You saw the laser beam on the eraser because the laser beam hit the eraser, and the red light was reflected, and it was reflected in a lot of different directions. In fact, you might as well stay up, because I'm going to be doing things.
All right.
Okay? And you all saw it because the beam was getting scattered when it hit the eraser. It was reflecting, and from all these different perspectives, you got some of that red light. Yeah? Okay? And now I've got a mirror. Okay? And I guess when I had the beam on the chalkboard, it was also scattering the light, right? You all saw the beam before, and we didn't really talk about it, but you saw it before, and then once it hit the eraser, you saw it on the eraser. Okay? Now I've got a mirror. Okay? I'm going to do the same thing. I'm going to take the beam of light, and I'm going to move it along the chalkboard until it hits the mirror, and let's look at what we see. Okay? So here's the beam of light. It's going towards the mirror. It hits the mirror. Now what do you see? because I've got chalk fingerprints on it. And if I hit the chalk fingerprint, you can see it. Okay, but if I go to the clean part of the mirror, you don't really see much of the laser dot. Okay, but you do see it on the mirror, or you do see it on the chalkboard. Okay, and in fact, if we follow it, what we get, you know, it bounces off. Okay, what we end up with is something kind of like that. See if I did it right. If I follow along like that, hey, look at that, not too bad. Okay? If I follow along and bounces off like that. Yeah? All right, so you can look at, you know, well, here's the surface of the mirror, and here's where the beam went, and the light ray bounces like that. And when it hits the mirror, it doesn't scatter, right? We didn't see the spot on the mirror, we only saw the spot on the chalkboard. So most of the light, you know, 98, 99% of the light, okay, is just bounced directly in this line, okay? And then where it hit the chalkboard, we saw it scatter, okay? So the mirror does something different with the light, okay? The mirror reflects it in an organized way, okay? Turns out, okay, and this turns out that if you measure this carefully, okay, you will find that this angle here and that angle here are actually the same angle. Okay, cool. So anyway, these are the same. And so you might think, oh, we're going to measure our angles like that with respect to the mirror. But it turns out that, and we'll see why a little later tonight, okay? It turns out that it's more convenient to measure your angles with respect to the perpendicular to the mirror. And when you do that, if these are the same, and these are right angles, then these angles here have to be the same. Okay? If this light ray is coming in like this and leaving like that, we'll say this is the incident beam. The incident ray. And we'll call this one over here the reflected ray. Okay. We'll call that the angle of incidence. Okay, and this one over here is the angle of reflection. Okay, and for a mirror, okay, so for a mirror, the angle of incidence is equal to the angle of reflection. And this perpendicular line, okay, we call that a normal. Okay. And this is sort of normal in the mathematical sense. Maybe you've run into this before. You probably, no? You probably ran into this when you were dealing with magnetism and induction, and you had the perpendicular surfaces or
normal force.
Or the normal force, right? The normal force in mechanics is, you know, when we talk about normal, what we mean is it's perpendicular to the surface. It's not that it's typical or usual or something like that. Okay, so this is, we'll measure it with respect to a normal line. Okay, the normal is perpendicular. Okay, cool. So, now, with the mirrors, where did I set my mirror? Here. Oh, okay. So with the mirror, you also yourself or see other people, depending on where it is. And that's kind of weird, at least, anyway, it's a property of the mirrors. And it's not a property, if I hold up a piece of paper, which also reflects light, you don't see images of other people in it, even though it's reflecting the light. And then, anyway, this is a property of the particular way that it reflects the light. And we can see how that works, okay, by doing the following. We can say, all right, here's a mirror, okay, or there's, I'm going to imagine that that's the surface of a mirror, and I'm going to put some object over here, okay, and well, let's just say that object is some sort of thing over there, and it's emitting light, right? Because this object is in a well-lit room, it's emitting light. Which way is the light going? Away. Yeah, it's diverging away from it, sort of as if it were a source. Okay? So, I'm going to draw my light rays red. One of the rays you might imagine might go like this. And another light ray, I mean, they go in all directions. Another one might go like this. And another one might go like that. Okay.
You guys are awesome.
We'll do one like this.
1, 2.
Okay. So all these rays
Times 3. You get it?
come from this dot, and they're going off towards the mirror. Now, if I want to figure out which way are they going to reflect, I have a way of doing it now. What I can do is draw a normal, okay, and then measure the angle, and then draw a reflected ray the way it's going.
I didn't know. Is it
And Monday and Tuesday.
Are you serious? Are we going to study?
And 1 hour. Just go to a month lab.
So I have these very big protractors.
We just have to participate. Dude, we just have to participate.
And I can go and draw my normal. I can put my protractor along the mirror,
Oh.
okay? And I can say, all right, I've got a 90-degree here. This one hits
That's the answer.
over like this,
That's what you guys
and
calculated.
just like that. This one actually is going and hitting the mirror pretty much at 90 degrees, almost.
It's a big portrait.
And this one is hitting it over here. Okay. So I can say, all right,
Are there showers at your gym?
this lets me draw my normals. Okay. I can say,
I need
there is one
to
here.
join a gym that has like a leg press.
Wait,
They're so
Here.
expensive.
pretty good for
They're like $1 million a month.
They have a big snap from right here.
Okay, and there's one there. All right, and now if I want to measure, if I want to go, well, which way is this ray reflecting? What I can do is use my protractor and measure that angle. This is at 10, 20, about 29 degrees. So I can say 10, 20, 29. So that's right there. This one is at 10, 18 degrees. So 10, 18, right here. Okay. This one is at about 3 degrees. Okay, so there's something coming off about there. And this one that. All right, and this one down here like that. So now, if I look at this pattern of rays that are coming off the mirror, they look like they're diverging from something. Yes? Because they look like they're coming from a spot. And in fact, if I were to say, if I put my eye here and looked in that direction in the mirror, I could say, this is my line of sight. Okay? Going back this across this ray. And when I see the mirror here, I see light rays coming off of it, and I see that I'm looking towards something, and if I didn't necessarily know the mirror was there, I would see that I would still see a ray coming at me this way. So as far as my brain is concerned, it goes, I see a light ray, it's coming from some spot, it looks like it's coming from somewhere over here. Okay? This ray looks like it's coming from somewhere over there. This one looks like somewhere over here. And this one
We're trying to make one with a bunch of milk cartons. 2 years now.
looks like there's some spot about right here, okay, that light rays are coming from, and it's not the object, okay, but these light rays look like the object because they originally came from the object. Okay, if this was a red object, they'd be red light rays. If it had, some funny little texture, these light rays would show that texture because they came from that object, right? Okay? But if I don't see these rays, okay, because these rays are going that way, and remember, rays don't interfere with each other, so because this one's crossing that one, all I can see is these ones that are coming at me, and they look like they came from over there. Okay? And so, in the mirror, okay, what I end up with is you look at yourself or you look at other things in the mirror, and they look like they're coming from some spot behind the mirror, and they look just like these other objects that are in front of the mirror. Right? So if I go over to this and move this around, okay, you should be able to see an image of the little red ball here in the mirror, as well as the little red ball. Yeah, and it looks a lot like the little red ball.
There's two of them.
What?
There's two of them.
It looks like two of them. Yeah.
Whoa.
Okay.
Another universe.
It's just explaining out.
Okay. So
That's why we see distance.
we'd say this is an image. Okay. We say this is the object. If all you can see is rays, what's the difference between an image and an object?
One's real.
One's real. What does it mean to be real?
Ooh.
You can touch it, right? Right. The object, if you actually went to that spot and stuck your finger there, okay, you would find the object, okay? But if you go to the spot where the image is, right, so if you're looking at this in the mirror, and you go, I want to go where the image is, and you stick your finger back here, it's not there, right? Okay? So the image is where, well, as far as the rays are concerned, the image and the object are the same thing. They're rays that look like the object that are diverging from some spot. If the object's actually there, we say it's the object. If it's not there, it's the image. So,
But how can you check to see if it is a reflection or if it is if you can't touch it?
what if you can't touch it?
Yeah.
Well, can you tell?
I don't know. Well,
Like if you were in a glass house of mirrors,
Yeah.
it's like, oh, which
That's
one?
right. Yeah, suppose you're in an amusement park and they got a house of mirrors, and all of a sudden there are a whole bunch of images of something. How do you know which one's the real object and which one's the image? Well, that's part of the problem. You got to bang into a whole bunch of mirrors before you finally get the object, because if they're good, clean mirrors, okay, and not wavy and distorted and stuff. So you go, this one looks like a real object, this one looks like it's in a crappy mirror. If they're good mirrors, you can't tell. Yeah? Have you ever, I watched my daughter do this recently, just walk into a sliding glass door, okay? Because she didn't see it at all, okay? Even though the object, it was sitting right in front of her. And, but you can, this happens with mirrors too, that sometimes, you'll have a big mirror, you don't know it's in the room, particularly like a restaurant or something, where they got one wall that's a full mirror. And it may be a while before you realize, hey, the restaurant's only half as big as I thought it was, because there's this mirror here giving this other image, and you, it really does look like that. So you can't tell. Okay, there isn't a, oh yeah, I know, those are image rays. They look just like it. It does turn out that it's possible to figure out where that image is behind the mirror. Trigonometry, yeah, we can do some trigonometry here. We can, this was geometric objects, right? Okay, and actually pretty simple trigonometry. One of the things I can do is I can say, I can do this. And say, let me extend my normal all the way here like this. Okay. And I could draw a perpendicular like this. Okay. I can draw a perpendicular over here like this. Okay. And I can say, well, here is this angle, which is the angle of incidence, and that equals the angle of reflection. Okay? But, again, using geometry, these are opposite angles of intersecting lines. This angle and that angle are equal. Okay? So if this angle and that angle are equal, then, and this is a right angle, and that is a right angle, okay? Then I can say that these are similar triangles. This angle has to be equal to that angle, okay? And if those are similar triangles, and then, let's see, these lines need to be proportional to each other, okay? So the length of this line, related to the length of this line is the same as the length of this line related to the length of that line. I can then, it's easier actually if I draw this one. I can make the same claim about these triangles, that this angle and that angle are equal. These are right angles, okay? These angles and that angles are equal. So these are similar triangles. They share this line, so this line has to be the same in both triangles. Then these are the same length, and these are the same length. Okay? So it turns out that this distance here, d, the perpendicular distance away from the mirror, is equal to this distance, the perpendicular distance the image is away from the mirror. So it's located just as far behind the mirror, okay, as the real object is in front of the mirror. Now, okay. And essentially what you're doing is saying that the object is producing rays, following which way they go, and then looking at where the image is. You can use this to answer all kinds of questions about what you would or would not be able to see in a mirror. Okay? Essentially, what you can do is just put the object at whatever location it's supposed to be at, put the mirror wherever it is, draw some rays, and see if you get diverging rays that look like they form an image. Okay? So, if I write out the rules for ray tracing, okay, say an object gives off diverging rays. Okay. Then you'd say the rays hit some object, and I'm going to write, if I wrote it for a mirror, I'd say they hit the mirror and the rays reflect with an equal, the angle of incidence is equal to the angle of reflection. But as we do this ray tracing in general, the rays are going to hit things, okay? It might be a mirror, it might be a curved mirror, it might be a lens, it might be a surface of water, it might be all kinds of different things. So it's going to hit some sort of optically interesting device, okay? So they hit some object, and the rays do, or let's say the rays follow the rule for that object. Okay? And then 3, what you do is you look at, you see if the rays diverge from a point. Okay? And then we'll say that is where the image is. Cool. So we can do this ray tracing for the next few days, right? We're going to do it as we talk about lenses. We're going to do it for other devices and that sort of thing. While we're talking about mirrors, what sort of things can be mirrors besides this?
Water.
Water, okay. Surface of water can be a mirror. So the light will reflect off the water, okay, and you can also be underneath the water and look out and see things, okay. So how does that work?
Surface tension?
Well, okay, there is surface. Well,
I mean, water's really only reflective when you have surface tension.
yeah. Well, it's kind of hard to have water without surface tension. But at the boundary, there's water and there's and there's air. And if the surface is calm, it'll be very flat like this, right?
Yeah.
Okay. And so it will reflect the light in an organized way, okay, like this mirror. Okay. It's also interesting that it lets some of the light through the as well. okay? So you can have reflection off the top of it that looks like a mirror, okay? And from underneath, you can see out, and you know, if you're like in a swimming pool and you look up, you can see other people that are outside of the water, okay? But when they look in, well, depending on how they're looking, they might see you, or they might see a reflection of the landscape up above. Does that sound like another kind of mirror? When you are hanging out in the drugstore and you decide you want to steal a pack of cards, how do they catch you if they catch you? They often
Loss prevention.
look, yeah, loss prevention. No, how do they do that? How do they know you did something if they're
Camera or?
yeah,
They have a two-way mirror.
But they used
window
to.
up
They
there.
used to be the cameras were expensive, okay, and so what they had was something that looked like a mirror, okay, in the store, and you could you know, you see yourself in the mirror, you feel like you're alone, okay, but it turns out that that there are other people behind it and they can see you. Now, how does that work? Could I do that with this mirror? No? Yeah, now if I sit behind this, I can't see through it, right? And over here, it looks just like a mirror. So you go, how do I get something that looks like a mirror in certain circumstances, but looks like a, but looks like a window in other circumstances?
Two different indices on each side.
Yeah? They're special, right? And they, well,
Like
it's,
you have like a lower end and more.
yeah, it appears that the light's sort of only going one way, but, yeah.
If you have two materials next to each other that have different indexes of refraction, one is going from high to low, another's low to high, so light will only go in one way.
Yeah, it seems like something like that will work, right? You ought to be able to take things and make a valve, if you will, that lets light only go one way and not go back the other way. But, and the changing the index of refraction will cause this inversion and phase inversion that we talked about. And it might cause a little bit of bending, but it doesn't cause the light to not reflect, okay? And so it ends up,
Does it give like a filter for certain kinds of light?
yeah, it's simpler than that, okay? And what's that?
Car, and the lights are on, and you can't see outside.
The deal is relative brightness, okay? So actually, what the mirror is really a lot like a pane of glass, okay? And you can see through it to the other side if if you have this situation, if you have glass, okay, and glass, if light comes in, some of it transmits, okay, and some of it reflects. Okay. And you can make glass that's sort of like half reflective, half transmissive, and it'll go either way, okay? But what you do is you make this side dark, okay? And if this side is dark, and not much light is getting through from the other side, and when it hits you, it scatters, okay? Then this end seems dark, okay? And this end seems light. And so mostly what you see is light that's reflected off of this, and this looks like a mirror. okay? And people can sit back here and they see the transmitted light and they don't have other light in here reflecting off of them. They're sitting in a dark room and looking out and they can see the store just fine, okay? So actually, it's really, the one-way mirror is really a two-way mirror, okay? It works the same on both sides, okay? But this side is really dark, and that side is really bright. That will happen in this room tonight, okay? If you look out that window, right now, it's kind of light out there, and it's kind of light in here. And right now, if you go outside, you can see in this room, and if you go, if you're inside, you can see out. But in about an hour and a half, it's going to be dark out there. And when it's dark out there, and we keep this room lit, when you look at the window, you're not going to see the bushes and the parking garage and stuff like that. What you will see is the reflection inside the room, and this window will look like a mirror. But when you go outside, walk around the corner and look in, and you'll see the lights and everybody inside. And essentially that window will become a one-way mirror. Okay? When you oh, right. So, if something out there is really bright, like a car's headlights or something, shining on the window, you will see that, okay? Because then the relative brightness has changed, okay? But as long as it stays dark out there, you won't see what's out there. If somebody in the darkened room, okay, in the drugstore, turns on a flashlight and shines it at the one-way mirror, you will see that, okay? Or if they turn on the lights in there, then all of a sudden you can see inside, okay? But as long as they keep the store brightly lit and that room not, you can't see. Okay? I'm trying to think of, well, other mirror things that are interesting to look at that we'll do in lab and homework and stuff deal with where you can see the images. And essentially, if you follow these rules, okay, and if you see diverging rays, then you will be able to see the image. If the diverging rays are not there, you won't. So let's look at another situation. Let's look at a curved mirror. So the idea here is that, let me get one. So you have a mirror like this, okay? It's curved, and so you can see images, but the image is kind of distorted. Right? We stole this from a convenience store. Okay?
Maybe it's because I'm not.
Unfortunately, they caught us on the one-way mirror. But it looks like the security in the convenience stores. This is another way. It lets you see things in this mirror different than a flat mirror. Okay? But we can follow the ray tracing rules, okay, and figure out how we find these images.
Oh my god.
So before I just drew a straight line and said that was the mirror. For a curved mirror, okay, what I would do is I'd say, well, there's some center of curvature of the curved mirror,
margin of error and the percentage
I don't know.
Conversion in there? Or the density there?
for our data.
Mirror I had was
And
different, it looked like this.
21.5%.
And some center curvature over here, and if I draw the shape, I have a curved mirror that looks like that, right? So here's my center, and here's the mirror. Okay? Now, I can say, suppose I have an object, and my object is over here,
Seems to.
It's a really big margin of error. Yeah. Yeah.
and I'm going to draw some rays that are diverging from the object. Right, there are three rays, they're diverging from the object. Okay? They hit the mirror, okay? And if it was a flat mirror, what would I say happens? They do what? They bounce back, and the rule for a flat mirror is, if I were to find the bounced ray, how would I find it? I'd measure the angle of incidence, and the angle of reflection would be equal to the angle of incidence, and I measure it using the normal, right? Okay? Well, it turns out this is a mirror, and if I look at a little bit of it, it seems pretty close to being flat, okay? And so, you know, at the spot where it hits, this is like a flat mirror. All I need to do is find the normal, okay? And the deal is the normal, or the perpendicular to the surface of a circle, is something that goes through the center of it, right? Any radius hits the edge of a circle perpendicular to the edge. Okay? So to find my normal, okay, I can just draw a line from the center here. Okay? Maybe it's longer than my protractor. My normal over here, looks like that. Okay? So these are my normals. Okay? For a flat mirror, it was the perpendicular to the surface. Well, it still makes a 90 degrees here. It's a little more difficult to find with a curved mirror because you've got to know the center, and the normal changes as you move along. With the flat mirror, the normal doesn't change. Okay. Now, if I want to find, if I say, all right, where is the image? Okay, I can then get my protractor and say, okay, this is about 10 degrees. Okay, so this one should be coming off at about 10 degrees over here. This one, the angle of incidence is 10, 20, about 31 degrees, 10, 20, 31. Okay, and this one over here, the angle of incidence is 10, 27, 10, 27. Okay, so I can find the reflected rays. Okay. This one goes like that. This one goes like that. And now by looking at my reflected rays, I've got one here, one here, one here. They do appear to diverge. Okay, if I follow their lines of sight back, the spot that they appear to diverge from is there, okay? So it's behind the mirror, okay, but it's closer in, okay? Another thing you might want to address with the ray tracing in the mirrors is this image bigger or smaller than the actual object, okay? Let me show how that would look for the flat mirror, okay? If you want to know if things are bigger or smaller, well, when I drew an object as a dot, it doesn't have any structure, right? So we can't tell if it's bigger or smaller. It's a dot is a dot, okay? But if I draw an object that has some structure, and typically what we'll do is something like this. We'll say, there's a little arrow here, really just so that we have one dot and another dot, and the arrow sort of indicates which one is, well, it's just, you know, this is the arrowhead dot, and this is the tail of the arrow, okay? If I want to find the image of that, I can do something like this. I can draw some rays from this dot, okay, and some rays from this one. I'm going to draw these in yellow. I can draw rays from this dot. Maybe in orange. Okay. And then I can figure out which way those reflect. Okay. I can draw my normals. So those are my normals, and then I can draw the reflected rays. Okay. For the yellow ones, I have this one over here that is 1024, 1024. Okay. This yellow one over here is 1022, 1022. And I can draw those in.
Thank you.
Like that. Draw this one in.
I've been reading, but I know it doesn't make any more sense.
Like that. I can follow its line of sight back. Follow this one's line of sight back. Okay. And I end up with, well, the image of that yellow dot is over here. Okay. And, thank you. Okay. And then if I look at the orange over here, I can say, this is 1022, so 1022. This orange one is 22, 1022, like that. Okay. And so if I follow the orange one, it goes that way. That one goes that way. And if I follow the lines of sight back, we say that orange one goes back here. This orange one goes like this, and so I'd say, the image of this dot is here, the image of that dot is here. Okay? And so these turn out to be the same height, okay? And they're in the same direction. Okay? That brings up a.
Because there's median and there's mean.
This mirror is kind of small. We need one of the bigger mirrors.
Median versus mean. I don't. I have a really bad finger on.
So here's a bigger mirror. You can see yourself, right? Now set it here.
The mean, yeah, that's the average. Mean with the multiplying.
Does the mirror, does the mirror reverse the image?
Mean with the sample. So I guess no.
But it's kind of a tricky question, right? If I lift up my hand in the mirror, right? If you're looking at me, this is, well, which hand is this? My right hand, okay? And if I stand over here and well, this is my right hand. So I stand over here and I raise up my right hand. And the image, this is to your right, correct? Okay? And when we look in the mirror, that image of the hand that's raised up is also to the right. Yeah? Okay? Have you heard people say, or have you thought, oh, things are reversed in the mirror? Uh-huh.
So you take like these two.
Yeah? And this can be, this certainly happens. You mind if I borrow your phone? The book says college physics, right? And I hold it up in the mirror, what do you see? The letters are reversed. How'd they get them reversed? It's kind of tricky, okay? But basically what happens is, where is the reversal? I show you this, and I say, I'm going to now show it to you in the mirror, and what's the first thing I do? I turn it around. Well, I just reversed it, right? If you could see from behind, it wouldn't seem reversed at all. Yeah?
Like a transparency.
Like a transparency. Thank you. Have you seen this before?
No.
No? Okay. That was the next thing I was going to do. Was go get a transparency.
You're so smart.
And,
Way to go, this thing.
I've thought about it.
Imagine we're in high school when we were young, just so annoying. That kid.
What kid is that?
Smart kid.
No, it's like we just that kid. One with those comments, you just want to like stop.
Just on the head of it.
Are you telling me to be quiet?
That was my brother. He would always read ahead on the next chapters, and then like in questions, they go like asking questions like, "How do you guys know what this means?" And he'd be like, like just tell exactly what it is, like. And then at one point he told me that one of the teachers got really mad at him because like he would just start confusing students by like answering in a way that would use like other things together. And I don't know. He was smart.
So do you have it open? I really didn't want to have to stay out of class.
Oh, no, I don't know.
This is the actual.
This is.
This is it. So where's the marginal errors?
Can't go anywhere.
okay, our transparencies are gone, but I found that transparent. All right, But here, I've written physics on this, yeah? And if I, can you see it? It's kind of dim, okay? And if I hold it up in the mirror, it's not reversed, yeah? Right? So the reversal, if I did what I did before and turned it around, of course it's reversed. But now it's reversed over here, okay? So the reversal, that, you know, when I say, look, I've got my right hand up, and then I go and look in the mirror, and I turn around, it's that turning around that's the reversal, okay? And so, you know, when we look at, you know, which end is up on here, okay? Oh, why does the mirror reverse? Why do we see this apparent reversal with right and left, but not up and down? Okay? It's because when I turn around like this to look in the mirror, but I don't stand on my head to look in the mirror. If I stood on my head to look in the mirror, then I'd see up-down reversal. Now? Good. Okay. And that puts us in a point where we can address this question of well, okay, so this object over here is the same height. It's going up and down. Is this one the same height? Or is it bigger, smaller? What's going on? Well, what I can do is draw a second point. Okay, I'm going to draw this one in red. Okay, and so we'll draw it down here like this. I'll just go ahead and draw two rays so it goes a little bit quicker. So I'll draw those two red rays. Okay. They're coming in like this. I will draw a couple of normals. Here's my center. Here's my normal. There. And there. And then I will, I need to measure. If I measure this, it's 20, there are 10, 20, 27, 10, 20, 27. And this one is 10, about 19, 10, about 19.
Just big.
I will draw these in their line of sight. And this one and its line of sight. So its intersection is about like that. So here is the height of the original object. Here's the image. Okay? So the image is closer in and smaller. Okay? So the image is not the same size anymore. Okay? As what it originally was. And that sort of makes sense when we look into this mirror. Right? They seem smaller, right? Okay, the images look smaller than what they did in the flat mirror. Do they look closer or further away?
Close.
Close?
It's farther.
It's kind of hard to tell. Yeah? So one of the issues, one of the reasons why it can be hard to tell is when things get closer, they appear bigger. When things get further away, they appear smaller. So if something's closer and smaller, you know, part of your visual clue is its size. If it's smaller, it must be further away, especially if it's an object that you know what its real size is, right? So if you see your face, you know how big your face really is, you see it in here and it's really small, you go, it looks like it's very far away. Now, how can you tell if something's really far away or really close?
A measuring stick.
Relative mirror. Mirror, big mirror.
So, for example, you compare it. Well,
How does
It's-
this look? For average deviation.
it turns out there's a pretty cool way to do this. Okay? Sometimes you're in a spot where this will work, sometimes you're not. Okay? So, which is closer, this bar or the meter stick? Okay? Okay? The bar, okay? You actually have a lot of visual clues that can help you out, okay? But suppose you didn't, okay? Or suppose you were afraid that these clues were misleading you, okay? Like you had, there were some optical devices like mirrors. Or suppose you're an astronomer and because they do this too, and you're trying to figure out which star is closer and which one's further away. Okay? It turns out that what you can do is if you can change your point of view, even by just a little bit, the relative motions of the two objects can tell you which one is further away. Okay? So if you can see both of these right now, and you move your head back and forth, what you will find is that the aluminum rod appears to do this. Try it out. Okay, and some of you may not be able to do this very well because you're standing in a bad spot. Okay, but it's a move. Like you might need to move it. But move your head a little back and forth, and you'll see that this one moves. That the aluminum one appears to move more than the wooden one. Okay, and if I switch the order, okay, now it reverses. Right. So and if they are in a particular spot, if they're lined up with each other, they move in sync. Okay? So it turns out that if we want to figure out where the location of an image is, and we want to know if we have, say, this mirror, and we think the image might be up close, but it looks to our eyes like it's far away, one of the things we can do is stick our finger where we think the image might be, and then where you can see it behind the mirror, and then move your head back and forth. And if what you find is that the finger and the image move together, then your finger's in the right spot. If the finger moves more, then the finger's closer. If the finger moves less, then the finger's further back. Okay? And so this is called parallax. Okay? And we can use it to tell which things are in front and which things are behind. Okay? By the way, astronomers use it with stars, okay? And what they, at least for, not for things that are like halfway across the universe, okay? But for things that are nearby in our galaxy, like say within a few hundred light years, okay? Then what they can do is look at a couple of stars that are close to each other in, say, the fall, and then again in the spring when the Earth is on the other side of the sun, and so that you change your perspective a little bit. And you can look at the relative positions of the stars. And the one that moves the most is the closer one. The one that moves less is further back. Okay? And by noticing how much it moves, okay, relative to the other ones, you can even figure out how far away it is. Okay. Cool. I want to do one more type of ray tracing, one more type of image to compare with this, and I'm going to do it over here so I can leave all of these up at the same time. So I'm going to draw another curved mirror. I'm going to say my center of curvature is here, and okay, there's my mirror, and I'm going to draw an object, say back here. We'll do something like this. Something like this, and we'll do this one in green, something like this. Okay? So I'm going to draw some yellow rays, okay, and they'll hit the mirror. Okay? And there, I'll draw another yellow ray down here, like that. Okay? And then a green ray. Draw one like that and one like this. Okay? Again, I can do the same rules. I can say there's going to be some reflection off that mirror according to the normal. I can draw the normal by using my center of curvature. I'm going to put a C here for the center so I don't mistake it for my other dots. And so I can draw a normal like that. Okay. I can draw a normal here. Like that. I can draw a normal here. Like that. And a normal like this. Okay. And now I can look at the reflected rays. Okay. For the yellow. I can look at my protractor. This is 11 degrees. So I can say 11. Okay. And over here, with my other yellow one, it is 5. So that's 5. So I can draw these rays. I can say, I've got one that comes like this.
I'll never talk to you again.
Okay. I've got another one here that comes like this. And these rays are going like that. Okay? Here's my object. The rays actually intersect here, okay, and they diverge from this spot. If I go over here and look at my lines of sight, they do not appear to come from another spot. So this image, instead of looking like it's behind the mirror, actually looks like it's in front of the mirror, okay, over here. And if I go back here and go, do I see any rays? There aren't any rays. It's just these lines of sight that make this image up, okay? But there are actual real light rays that are coming through here, okay? We'll call these types of images, we'll say they're virtual images. Okay? And this over here, that's a virtual image, that's a virtual image. Okay? And so it's created only by the lines of sight. The actual light rays don't go through the point where the image is. But this one over here, the light rays actually do go through the point. So we'll call that a real image. And I can trace this green one and say, okay, the green, oh right, I measure. We get the protractor and measure the green over here. I can say that is about 2 degrees. So that's about 2 degrees over here. And the other green one is down here. And this is 9 degrees. So that's 9 degrees over here. And I go, the image of the green dot is over here. So if I were to say, all right, if I started the green dot and made my little arrow point at the yellow dot, okay, the image would look like this. It starts at the green dot, it points at the yellow dot. And so the image is upside down, okay? So this is sort of different than what happened last time. You know, with these images over here, what we ended up with was virtual images, and if I red dot to yellow dot, those, if it starts pointing up, it ends up pointing up. Those point up. That one does not. It flips the image over, okay? So here's a mirror like that, okay? And if you look in this, I'll sort of move around because you got to get kind of close. Do you see yourself in it upside down? Yeah? Yeah? Yeah?
It's like a window to Australia.
Yeah? Upside down?
See like that. Right there.
Good?
This is some cool kids back in the day.
Yeah? See? It flips it over.
She's not cool.
So you get a lot of different effects from the mirrors, and we can follow it with the ray tracing. Okay, so let's now do our informal lab. This is the reflection of light. Informal lab. Okay. I will bring out a cart that should have mirrors and things like that. You may want some paper to trace rays on, okay? And I located this. Okay, this is what I wanted for the interference, but at least I found it now for ray tracing. We've got this large fanfold paper. So if you take like a couple sections of this and put your mirror here and start tracing lines, you can get a nice big paper area to trace rays on. So feel free to grab a few sheets of this paper to do your ray tracing. For this lab, a lot of what you're going to hand in is your ray tracing documents. Okay? So when you do this, make this a part of the record that you hand in. Okay? Cool. I'll go ahead and start getting things out, but go ahead and get started.
Oh, probably.
Oh, maybe you hear us probably.
What happened?
You're talking
Door busting up?
There's more things on this screen than you actually This is where they are.
There you go, frame one out.
I mean, we can
Which
just
one? Reflection of...
reflection
Of light.
4. Introduce the idea of a physical model, the light ray, in this case, to apply the model and gain understanding of the light, experiment one investigate the reflection. Okay.
And I found the transparencies, they were on the tray. So if you want to look at a transparency in a mirror, here's one with writing on it.